The following is a demonstration of an automated AI workflow, producing a full documentary from a single thesis statement. This workflow used OpenAI o1 Pro to write background research prompts, given the thesis statement. Deep research generated full reports with references, and these are provided at the end of the video. o1 Pro wrote a script through several iterations of self-revision. A Python application was developed with o3 Mini to manage asset generation for the script, including TTS audio using OpenAI Onyx and breaking sections into discrete concepts for image generation prompting. A few hundred high-definition DAL 3 images were obtained and then assembled automatically with transition effects. No human editing was performed on the main body of the video. It is essentially 100% AI generated. The spoken content is likely factually accurate, but this is not intended to be a source of scientific information. I have included links to talented and skilled experts in the video description, and I urge you to visit them. AI images are not accurate, but are whimsical dreamlike representations based on the context of the content being presented. Enjoy the often ridiculous and sometimes surprising slideshow.
From the cosmic tapestry of finely tuned physical constants to the specific events that shaped our solar system, this narrative examines how countless narrow gates allowed life and ultimately human civilization to emerge. We begin with the astonishing balance among the fundamental forces and the razor-thin margins of cosmic evolution that made stars, planets, and complex chemistry possible. From there, we trace the chain of fortuitous conditions, from Earth's formation in a habitable zone to the stabilizing presence of the Moon and protective shields like the magnetosphere, each step as improbable as it was essential. This journey continues through climatic upheavals, mass extinctions, and population bottlenecks, culminating in the rise of a species capable of shaping its own destiny through agriculture, industry, and beyond. In every chapter, the margins seem impossibly slim, underscoring the extraordinary improbability of our existence. They say the universe is everything, but it is also the cradle of possibility. From the smallest atom to the largest galaxy, a delicate balance of physical laws once allowed complex organic life to emerge. It was as though the cosmos itself passed through a series of narrow gateways, each an eye of the needle, that led to biological existence on at least one small planet. Imagine reality as a machine with countless dials, each a fundamental constant of nature. If any dial had been off by even a tiny fraction, the entire structure could have collapsed into sterility. No stars, no stable atoms, no life. Scientists point to these dials, like the strength of gravity, the nuclear forces, and the electromagnetic force, and marvel at how they all land in the precise range needed for complexity to blossom. This fine-tuning is considered a cosmic coincidence, so precise it feels almost orchestrated. Within every atom's nucleus, protons and neutrons are bound by the strong nuclear force. Slightly stronger, and protons might fuse too easily. Slightly weaker, and heavier elements like carbon and oxygen might never form. In the actual universe, the force was tuned just right, somewhere within a tight margin, allowing both hydrogen to remain abundant for star formation and heavier elements to be forged later inside those stars. Gravity, too, danced between extremes, strong enough to gather cosmic matter into galaxies and stars, yet weak enough to let those stars shine for billions of years. Similarly, electromagnetism sits at a delicate balance that permits atoms to hold electrons, yet also allows for the complex chemical bonds essential to living structures. A small deviation in any of these forces would have left planets barren, no organic molecules, no evolving lineages of life. Then there is dark energy, tied to the cosmological constant, which drives the accelerated expansion of space. Observations revealed this constant to be tiny but not zero, any larger, and galaxies might never have formed. Leonard Susskind calls this the knife edge of existence. Indeed, each constant of nature occupied a razor-thin band that allowed stable atoms, long-lived stars, and eventually living organisms. If one dial had shifted slightly, there would have been no chance for life's story, nor any successors that might look back on these coincidences. From cosmic fine-tuning, attention turns closer to home. One star among countless gave rise to a system of planets. That particular star system had to align with similarly improbable conditions to support the home world where organic life flourished. So the journey continues to the solar system, where about 4.6 billion years ago, a new chapter began. Around 4.6 billion years in the past, a vast cloud of gas and dust, enriched by earlier generations of exploding stars, collapsed under gravity in one region of the Milky Way. The pressure in its center grew so immense that hydrogen began to fuse. Thus was born the Sun. Meanwhile, surrounding material formed a swirling protoplanetary disk of collisions and clumps, out of which emerged the planets. The location of this stellar nursery in the Milky Way was also crucial. Not too close to the galactic center with its intense radiation, nor too far in the galactic outskirts where heavy elements are less abundant. It was a sort of galactic Goldilocks zone, containing enough metals and heavier elements to create rocky planets. Within that disk, smaller grains stuck together, becoming planetesimals. Some merged into gas giants, others into smaller rocky worlds. One such rocky world was Earth, occupying an orbit within the Sun's habitable zone, neither too close nor too far. Slight deviations in that orbit might have led to a superheated surface or a frozen wasteland, but the trajectory settled in a place conducive to liquid water. That delicate positioning set the stage for Earth to become a cradle of biology. Another stroke of luck arrived in the form of Jupiter, a massive planet that formed early. Its gravitational interplay may have cleared the inner system of super-Earths or excessive debris. Jupiter also continued to shield Earth from frequent asteroid and comet impacts. Though hardly perfect, its protective influence helped preserve a relatively stable environment, an essential factor allowing fragile life to gain a foothold. Observing this arrangement underscores how many elements had to align. A slightly different mix of heavy elements, a different migratory path for Jupiter, or an altered distance from the Sun, and Earth might never have become the nexus of evolution. But Earth did emerge, shaped by cosmic dust, guided by gravitational neighbors, just one improbable step in the long chain that would eventually yield organic life and beyond. Not long after Earth's formation, a Mars-sized body, often called Theia, collided with the early planet in a direct, catastrophic impact. Debris from this collision coalesced into a single satellite, the Moon. Far from a random chunk of rock, it profoundly shaped Earth's path toward habitability. That giant impact stripped away much of Earth's primordial atmosphere, preventing a possible runaway greenhouse effect that might have sterilized the surface. In the aftermath, the Moon served as a stabilizing force on Earth's axial tilt. Without lunar gravitational torque, Earth's tilt could vary chaotically over millions of years, driving extreme climate shifts that might have doomed the development of complex species. Instead, the Moon helps keep Earth's seasons relatively mild and predictable. The Moon's pull also generates ocean tides, a subtle force that drove coastal and tidal zone life to adapt in inventive ways. Early organisms learned to cope with changing water levels, salt concentrations, and exposure to air, and these adaptations later aided the colonization of land. Even Earth's rotation has been slowed by tidal friction, lengthening days from a few hours to the current 24-hour cycle. This diurnal rhythm profoundly shaped the evolution of countless life forms, influencing behavior, metabolism, and photosynthesis. No other rocky planet in the inner solar system has such a large companion relative to its size. Mars's tiny moons and Mercury's moonless sky lack the stabilizing benefits Earth enjoys. Thus, the Moon stands out as another improbable stroke of fortune, a protective sentinel born from cataclysm, yet vital for life's steady progression. With the Moon in place, Earth still faced numerous hazards from solar radiation to cosmic rays. The next chapters detail how Earth developed two critical defense systems that shielded emerging life from lethal assaults. Space is unforgiving. Radiation, charged particles, and ultraviolet light could sterilize a fragile world. Remarkably, Earth formed two robust lines of defense. One is an invisible magnetic shield generated by the planet's molten core, The other is an upper atmosphere layer of ozone that absorbs dangerous UV radiation. Deep within Earth, churning iron and nickel create electric currents that sustain a global magnetic field. This magnetosphere envelops the planet, deflecting solar wind and preventing the atmosphere from being stripped away. Mars, which lost its global magnetic field long ago, provides a stark warning. Solar winds slowly eroded its once thicker atmosphere, transforming a potentially habitable world into a barren wasteland. Earth, by contrast, maintains its magnetic barrier, a silent guardian that has endured for billions of years. High in the stratosphere, the ozone layer forms another protective veil, blocking most of the sun's harmful UV radiation. This shield materialized only after photosynthetic organisms began releasing oxygen into the atmosphere. Ozone is essentially three-atom oxygen, O3, superb at filtering UV rays. Without it, Earth's surface would be bombarded by DNA-damaging light, a dire scenario for any aspiring land-based life. Neither the magnetosphere nor the ozone layer was guaranteed. Had Earth's core cooled more rapidly, or had oxygen-producing microbes never proliferated, these defenses might not exist. Life, if it persisted at all, would likely remain confined to sheltered niches. Instead, Earth boasts robust shielding that allowed life to flourish in diverse environments. With these protections in place, the planet became an arena for increasingly complex organisms. But how did Earth's atmosphere become oxygen-rich in the first place? The next section delves into the Great Oxygenation Event, a billion-year saga that transformed the planet's chemistry and set the stage for advanced forms of life. For nearly half of Earth's history, its atmosphere was devoid of free oxygen. Early microbial ecosystems relied on other metabolic pathways. That changed around 2.4 billion years ago, when certain microbes developed the ability to split water molecules using sunlight, releasing oxygen as a byproduct. Though mundane in hindsight, that oxygen shift was momentous, the Great Oxygenation Event. Initially, oxygen produced by these microbes was chemically captured by oceans and crustal minerals. Only after the supply of reactive minerals dwindled did oxygen begin accumulating in the atmosphere. This accumulation was catastrophic for many anaerobic life forms, which found oxygen toxic. Vast populations perished, arguably Earth's first mass extinction. Yet for those that adapted, a high-energy form of respiration opened new doors, eventually supporting larger, more complex cells. Over immense spans of time, atmospheric oxygen levels rose sufficiently to spawn the protective ozone layer discussed earlier. This, in turn, allowed life to venture onto land. The emergence of oxygenic photosynthesis may have been a one-time evolutionary stroke of luck. Absent that innovation, Earth could have remained locked in a low-energy state, forever dominated by simpler microbes. Instead, the Great Oxygenation Event stands as a pivotal threshold. It destroyed whole ecosystems while simultaneously igniting the potential for new and more diverse life. From that point onward, Earth's biosphere would be powered by the dense fuel of oxygen-rich air and waters, setting the stage for leaps in complexity. However, this oxygenic world would soon face climatic extremes that threatened to derail the entire experiment of advanced life. Next, see how Earth narrowly avoided both runaway heating and global ice ages, calamities that could have snuffed out the evolutionary gains oxygen provided. As oxygen built up, Earth's climate teetered between extremes. One potential fate was a runaway greenhouse effect, akin to what befell Venus. In such a scenario, temperatures soar uncontrollably, oceans evaporate, and the planet bakes under thick clouds of water vapor. Yet, through geological and biological feedback loops, such as carbon burial and the balancing role of photosynthetic organisms, Earth dodged this hothouse endgame. On the other side of the spectrum, Earth endured multiple episodes of snowball Earth, when ice advanced from the poles nearly to the equator, locking the planet in a deep freeze. Volcanoes, still active beneath ice, vented carbon dioxide over millennia, slowly building greenhouse conditions. Eventually, a tipping point was reached, and rapid melting ensued. If the ice had persisted indefinitely, photosynthesis could have collapsed, dragging oxygen levels down and stalling multicellular life. Earth somehow maintained a precarious balance. Each global freeze ended, each potential runaway greenhouse was reined in. If conditions had tipped too far in either direction, life's story might have ended with microbial forms clinging to slim refuges, or no life at all. This resilience highlights how a planet's climate system is subject to complex interactions among atmosphere, oceans, geology, and biology itself. With these climate gauntlets behind it, Earth was poised for further evolutionary experiments, at least until the next great challenge, mass extinctions. These events repeatedly reset the clock, wiping out dominant life forms and opening niches for new ones to rise, including the mammalian lineage that would one day include a tool-making, world-altering species. Life's progress on Earth was neither smooth nor guaranteed. Cataclysms, some triggered by volcanic upheaval, others by asteroid impact, devastated ecosystems again and again. Each mass extinction carried the risk of unraveling evolution's progress. Yet each time, a handful of survivors clung to life, eventually proliferating into new adaptive radiations. One of the most severe events came about 252 million years ago, the Permian-Triassic extinction. Over 90% of marine species and a majority of land species vanished, likely due to massive volcanic eruptions releasing vast amounts of greenhouse gases. Oceans acidified, temperatures soared. A few proto-mammals survived, sheltered by happenstance and perhaps by warm-blooded traits. This narrow survival allowed them to evolve in novel directions once the crisis passed. For tens of millions of years, though, dinosaurs reigned supreme. Mammals remained small and nocturnal, diversifying quietly underfoot. Then, 66 million years ago, an asteroid struck, abruptly ending the dinosaurs' rule, except for the ancestors of modern birds. With dinosaurs gone, mammals seized vacant ecological niches and rapidly expanded. Among them were early primates, which, over time, gave rise to hominins. These repeated catastrophes acted like evolutionary filters, wiping away dominant lineages while inadvertently granting new ones the chance to flourish. The mammalian lineage that eventually spawned a big-brained primate owes its existence to these churns of fate. Yet even that primate would face repeated brushes with extinction, episodes that might have ended the story before it truly began. Among the diverse mammalian branches that spread after the dinosaurs' decline was a group of primates that gradually acquired traits setting the stage for complex thought. The shift to bipedal walking freed hands for tool use. Living in intricate social structures spurred intelligence for cooperation and competition alike. Over many generations, iterative improvements, cooking food to release more nutrients, refining stone tools, developing rudimentary language, compounded, enabling a species to wield mental powers unlike any other on Earth. This evolving cognition did not occur in a vacuum. Environmental pressures, such as shifting climates and resource scarcities, continually tested ingenuity. Innovations in tool-making or social organization paid immediate survival dividends, reinforcing a feedback loop. More efficient foraging supported bigger brains, which in turn enabled finer cooperation and communication. Eventually, symbolic language emerged, granting the ability to share abstract ideas and coordinate strategies across larger groups. Over time, art, ritual, and advanced technologies blossomed from these mental foundations. Looking back, each evolutionary step, bipedalism, fire use, tool-making, language, was a narrow gate in its own right. Miss any one link, and the chain leading to advanced societies might never have formed. Yet even with growing cognitive capacities, this lineage nearly vanished multiple times. Genetic evidence indicates that population bottlenecks, possibly triggered by severe climate events or volcanic eruptions, drove numbers of Homo sapiens perilously low. One notable crisis involved the massive Toba eruption around 74,000 years ago. That supervolcano expelled ash and aerosols on a colossal scale, potentially causing a volcanic winter. Ecological collapse may have whittled human groups down to just a few thousand individuals. Had circumstances been even slightly harsher, Homo sapiens might have faded from the evolutionary record. Another bottleneck appears to have occurred about 900,000 years ago, when shifting climates reduced habitable regions, forcing small, isolated groups of hominins to survive in scattered refuges. Over many millennia, they rebounded, carrying genetic traits that would eventually define modern humans. Crises like these accelerated adaptations in tool use, social cohesion, and innovation, traits that served as lifelines in times of dire scarcity. These brushes with extinction underline humanity's fragile beginnings. Even with intelligence and cooperation, survival was never guaranteed. The species emerged from each bottleneck slightly altered, more adept at problem solving. In this way, adversity shaped the minds that would later cultivate agriculture, build cities, and probe the mysteries of the universe. Then came the Holocene epoch, a warm and unusually stable climatic phase beginning about 11,700 years ago. In that window of relative predictability, certain groups of humans began cultivating crops and domesticating animals. This shift from nomadic foraging to settled farming ushered in massive societal transformations. In regions like the Fertile Crescent, wild grains and reliable water sources encouraged experimentation with planting seeds. Over time, deliberate sowing and selective breeding replaced chance harvesting. Domesticated livestock offered labor, meat, and hides, and surplus harvests supported growing populations. Villages formed around these new food sources, then expanded into the first towns and cities. Agriculture was far from certain. A more volatile climate could have derailed early attempts at sowing and harvesting. But during the Holocene, temperatures and rainfall patterns stabilized enough that once risky farming became feasible. Humans, in turn, developed permanent settlements, social hierarchies, and specialized trades. The food surplus unleashed extraordinary innovation, laying foundations for writing, mathematics, and large-scale architecture. This Neolithic revolution was another narrow gate, reliant on a rare stretch of climate stability, a handful of domesticable plant and animal species, and the ingenuity to harness them. From this agrarian base, societies flourished. Yet those same societies soon faced new challenges and found a powerful ally beneath the Earth's crust in the form of fossil fuels. For millennia, civilizations relied on muscle, wood, wind, or water to power daily tasks. These energy sources placed natural limits on production and transportation. Then humans tapped into ancient stores of compressed sunlight. Coal, oil, and natural gas formed over hundreds of millions of years from long-buried organic matter. In 18th century Britain, a shortage of firewood spurred a turn to coal. Steam engines soon pumped water from coal mines, creating a feedback loop of rising coal extraction and improving steam technology. Factories no longer needed rivers for power. They could set up anywhere coal was delivered, fueling mass production. The momentum spread worldwide, igniting the Industrial Revolution. Later, oil emerged as a dense, portable energy source, powering internal combustion engines in cars, trains, and ships. This unleashed unprecedented mobility and global trade networks, binding continents into a single marketplace. Societies grew in complexity and reach as fossil fuels drove production, communication, and transportation on scales unimaginable in earlier eras. Yet the availability of these geologically rare deposits, combined with just the right technological leaps, was neither guaranteed nor inevitable. If Earth's deep history had not locked away vast carbon reserves, or if certain inventions had failed to emerge, industrial-scale economies might never have taken hold. But take hold they did, propelling human society into a modern age of skyscrapers, space travel, and digital networks. Yet even the era of fossil fuels is just another chapter in our improbable tale. Today, we grapple with sustainability and wonder how to power future progress. As we look back, we realize our species has repeatedly slipped through narrow gateways: cosmic, planetary, and climatic. The rise of a global, technological society has depended on a near-miraculous chain of events. From the first spark of the universe to the coal fires of the Industrial Revolution, each link had to hold for us to stand here, at the edge of whatever comes next. Looking back, the story of life on Earth, and indeed of civilization, rests on countless convergences of chance and necessity. From the exquisite calibration of cosmic forces to the delicate planetary equilibria that kept Earth both habitable and dynamic, every turning point could have led elsewhere, or to no life at all. And yet here we stand, heirs to a universe that threaded a million cosmic needles to produce stars, biospheres, and self-aware minds. As we grapple with the new challenges of our own making, this perspective offers both humility and inspiration. Humility in recognizing how fragile the chain of events was, and inspiration in realizing that the same intelligence and cooperation that guided us through history's narrow gates may yet help us safeguard our future.